This is the screencast for section 6.5, example 4. So I'm going to read to you a little bit. We have seen the exponential growth at the beginning can be modeled by the differential equation dp dt equals k times p. So in other words, the derivative equals a constant times the output. For some k greater than 0, we have to find that constant. If we want the growth rate to approach 0 as p approaches a maximal carrying capacity m, we can introduce a limiting factor of m minus p. So in other words, our growth rate would be increasing at first, but then the growth rate would approach 0 and level off if we have this m minus p factor. That's logistic differential equation. That's how logistic growth is formed. So here's where we get to study logistic differential equations for logistic growth. So example 4 says the growth rate of a population P of bears in a newly established wildlife preserve is modeled by the differential equation dp dt equals 0.008 p times 100 minus p. So you can see that we are dealing with logistic growth. The rate of growth will approach 0, where t is measured in years. So A says, what is the carrying capacity for bears in this wildlife preserve? Well, the maximum carrying capacity that we saw in the previous screen is this m value here, 100. So that would be 100 bears. That is the carrying capacity for bears in the wildlife preserve. The environment can't support any more than 100 bears. All right, so B, what is the bear population when the population is growing fastest? Well, when it's growing fastest, it's going to depend on the first derivative. So I will take that first derivative. I'm going to distribute to make it a little bit easier, and I want to find out when it is growing the fastest. So I want to find out the rate at which it is growing, so I need the derivative of the derivative. So I'm going to take the second derivative, which would be 0.8 minus 0.016 p. See how that was easier to take the derivative after I distributed stuff? Fine. So now I'm going to set that equal to 0, and I get that p equals 50 when p double prime, that would make p double prime 0. So now I'm going to test to the left of 50, and I get positive, and then to the right of 50 is negative. So in fact, 50 is a maximum of p prime, because its derivative, p double prime, changes from positive to negative. So that is when the population is growing, the rate of growth is the fastest. So the second derivative changes from positive to negative. A maximum on p prime, 50 bears. Part C, what is the rate of change of the population when it is growing the fastest? So now we want to find the rate of change of the population at 50 bears. So in that case, I can use the first derivative, the rate of change of the population, so the derivative of the population, dp dt, and plug 50 bears into that and get that it's changing at a rate of 20, and that would be bears per year. So now try problem number 25. Says the logistic equation describes the growth of a population P where T is measured in years. In each case, find A, the carrying capacity of the population. Alright, so the carrying capacity, I can tell that I'm not just dealing with exponential growth, but now I'm dealing with logistic growth. And that M value, 1200 bears, is going to be the limit to growth, or the maximum carrying capacity. We used to call it limit to growth in pre-calc. It means the same thing. And then part B, find the size of the population when it's growing the fastest. Alright, so when the population is growing, that's dp dt. The fastest, the rate it's growing, I need to test the second derivative. So first I'm going to distribute the 0.0002 p into the binomial, and now I'll take the second derivative, set that equal to 0, find the p-value that makes it equal to 0, and now test that on a number line for p double prime. So at 600 individuals, there could be a maximum of dp dt, as long as the second derivative, dp dt's derivative, changes from positive to negative. So I'll test the left of 600, I get positive, the right of 600, I get negative in p double prime here. So in fact, there is a maximum of dp dt at 600 individuals. So I can say that the population is growing the fastest when there are 600 individuals. There is a maximum of dp/dt. Part C, find the rate at which the population is growing when it's growing the fastest. So at 600 individuals, I want to find the rate at which it's growing. So I want to find dp/dt. So I'm going to take dp/dt, plug in 600, and I get 72, and that would be individuals per year. So basically, we're looking at the original function as logistic growth. The population function, or just P, is a logistic growth function. Then dp/dt, the derivative, is going to be a parabola with its maximum, kind of right about there at 600 individuals. And then finally, the second derivative is going to be linear. You can see that from the equation. And it's got a 0 here at 600 individuals. Basically, that is what I tested throughout this problem.